Hello, this video is about an example of modules, of the notion of modules of the polynomial algebra in one variable, with coefficients being a field. So this concept of a module is a useful one in ring theory, and abstractly it's just an action of the ring on an abelian group satisfying certain properties, bilinear, so linear in this argument, linear in this, and associative. And let's just introduce some notation for this action we have. So we're acting on an abelian group M with polynomials, and the result is this. So any polynomial acted on M will give us another element of M, which will be denoted this way. So we will unpack this definition for the specific class of rings and see what they are in the easier terms. That will come after the separator. So the first to observe is that we have an action of an easy part of the polynomials, namely scalars. So we have f module structure on M, and that is this action, and that is straightforward to see that this is just a structure of a vector space. Of the field F on M. So we are allowed to multiply our vectors by scalars. And the scalar multiplication is linear in vectors, linear in scalars, and associative, and that is what makes a vector space. The second bit of structure, which is inevitable if we have a module of a polynomial ring, is we should be able to multiply with the polynomial which is just t. So this multiplication by t, let's see what it is. Well, it's a map from our module to itself. Right, this is just the rule. If we know how to multiply with arbitrary polynomials, we should know how to multiply with the polynomial t. And I'm claiming that this operator is a linear operator with respect to the vector space structure, which is already we discovered by looking at how scalars have to act. So what does it make a linear operator? Well, it has to be preserving sums, so sending sums to sums. Well, that is a part of the module deal, that is the linearity in the module variable. And then it has to commute with scalars, and of course it does. So it says that in our definition of the operator, it says that multiplying with the scalar and then with t is the same as multiplying with t and with scalar. Well, both are multiplying with t times c. It doesn't matter which order we put t and c, it's the same polynomial. So it has to commute with scalars. And that is an inevitable consequence of having a module structure over the polynomials. What I'm going to argue is that is all we need to know to reconstruct the full module structure. Just two little pieces of data. A vector space structure on our module, and then this linear operator. So here is this argument, this reconstruction. Now we want to see how an arbitrary polynomial should act on our vector space. So let's write down a template for a polynomial. So we have some coefficients, we have some powers of t put together in a sum. That's what polynomials are, after all. And we want to compute what is the result of action of this arbitrary polynomial on M. Well, let's just use module rules of the game, of this action. they say that if we have a sum acting on M, we can rewrite it as a sum of pieces acting on M, and each piece is this monomial combination of powers of t and the coefficients. And multiplying by coefficients, we already packaged into being a vector space. So we're down to multiplying with powers of t. But multiplying with powers of t is iterating multiplication with t. And we know how to do it. We call it t. So this is the definition of what is t applied to m. And then rewriting, finally, we'll have t iterated. So iterated multiplication will be corresponding to this iteration of the operator on m. And that is, we can think of as one operator, and in linear algebra it's very useful, so it is called just the polynomial with t substituted to it. And that is the one operator we see here. So that is how this polynomial evaluation of polynomials on operators is defined in the first place. We just think of the combination of powers of this operator we substitute in the polynomial times coefficients of the polynomial taken the sum of. And that's what we see acting on our m. So that is the definition of the action of an arbitrary polynomial if we know how to act with the polynomial which is just t. So hence this reformulation. A module is the same as a vector space together with a linear operation. So now let me do something else. Let me describe in a similar fashion modules over quotients. Quotient rings of this polynomial algebra. So what are quotient rings? If we have coefficients being a field, then they're all quotients by ideals, and all ideals in this case are principal, so they're generated by single element. Let me start with this, say, generator, and define my quotient ring this way. So these are all polynomials, but I'm declaring the polynomial h chosen one to be 0, and everything else which comes from that declaration is also 0. So all products of h with anything will be 0. And now I'm to unpack what is to be module over such ring. Well, first unpacking is, if we have an action of this quotient, we can think of it as an action of the unquotient ring. So first it is module over the polynomial algebra. And then we declared in the quotient that h is 0. That is the meaning of the quotient procedure. So this declaration has to be remembered by saying that this polynomial acts as 0 on any vector, so on any module element. And now we are transitioned to this alternative way of looking at modules over the polynomial ring and say that M is a vector space and then together with a linear operator, this t, and the final condition is that given polynomial h is killing everything in the module, will translate according to this rewriting rule in the condition that if we compute h of t, that will have to act on any vector in a 0 way, so that will have to be the 0 operator. So h of the polynomial t is 0. Just a quick example. Let's take the quotient by the polynomial, say, t squared minus t. So according to this rewriting rule, a module over such quotient is a vector space over the ground field F, together with the linear operator. And the condition is that t, the operator squared, is equal to t. So we call such operators projectors, and that is having a projector on the vector space is the same as being as giving a module structure with this quotient ring. So I'll stop here.